Welcome back to ECE 442-542. We are now in the fourth quarter, meaning we've just completed our third exam, and the last exam is the final exam, and that occurs on the last day of finals, the 10th of May. And before that, we will have a couple of more homework assignments. Homework 7 is due on a different day. It's due on a Saturday, so that it's not due during the last week of class. Homework 8 will be, but that one I think I'm making optional so that I don't have a homework due during the last week of scheduled class time. Teacher course evaluations, you've probably been getting emails. Is that true? Yes? No? Should be getting emails relative to teacher course evaluations, and those are very helpful to me in terms of trying to determine how to improve the class for the next set of students that move through the curriculum or this particular class. And we will today, our goal is to complete the rules. We're in the fourth quarter, so we have to have rules. We're now going to see rules 4 and 5 for the root locus. We've done rule 1, 2, and 3, and now we'll do rules 4 and 5. And if you want analysis, more resources for that, you can check the Shams outline. That's chapter 13. The design using the root locus strategy is chapter 14. And we'll hopefully get through some examples and illustrate these different rules and the way to apply them. But before we do that, what I want to do is really simply communicate what those rules are. Try to state those so that you can at least have them in front of you, and then we'll figure out how to apply them. Here is our generic block diagram, and in this block diagram, we've pulled all of the different pieces of our system and controller except for the adjustable gain parameter K. And all of those controller and plant pieces, those factors, are now in this factored form, and we could actually have a gain in there, but I haven't shown it. We've maybe incorporated that into the gain K. But we have now this adjustable knob K that we're using, and this is now the notation that we will use to describe or talk about rules 4 and rule 5. And the main thing to keep in mind is that we have Michigan zeros, M, subscript M, and we have Nevada poles, N, for the subscript on the number of poles. So we have M and N, but you may not be able to distinguish my M from my N, so I may say Michigan and Nevada. Maybe you can make the distinction between those two. Rule number 4 concerns asymptote lines. It's not the actual branches. In some cases it is, but in general, these are guidelines. That's why they are called asymptotes, meaning our branches approach those lines asymptotically. Rule number 4 says that the asymptote lines are guidelines for sketching the branches of the root locus that approach the infinite zeros. And we know how many infinite zeros we have given the number of finite zeros and the number of poles, finite poles in our system. And we are to establish notation. We will go ahead and let Pz sub E be the pole zero excess, which is simply the number of poles, Nevada, minus the number of zeros, Michigan. That's Pz sub E. And that's also equal to the number of zeros at infinity. You can think of it both ways. You can say, oh, the pole zero excess, or you can say the number of zeros at infinity. They're the same number. And someone has asked me about infinity, and I hope it's clear. I've just sort of assumed that it was clear, and maybe it wasn't. If this is our z-plane, Where is infinity? The point that I wasn't appreciating before the student came up and asked was, well, here's plus infinity and here's minus infinity is what they were thinking when I said, oh, it's going off to infinity. But we need to now think more globally about infinity. Infinity could be in the imaginary direction. It could be up here. Infinity could be in the negative imaginary direction. And in fact, infinity is any point that goes off to infinity in any direction in the z-plane. That's what we mean by z going off to infinity. It can go in any direction. It's just going there at a very far distance, obviously. It's an infinite distance away from the origin. Infinity means that we're somewhere on this distance where we're letting r go to infinity. Is that clear? So when I say zeros at infinity, they could be going in many different directions. It's not just the 1, 0 that might be zipping off at minus infinity on the real line. It could be going in any particular angle. And the reason that's important is because these asymptotes that define these guidelines are going to be assuming particular angular values. And this tells us what those angles are. The angles of our asymptote, which we are labeling phi sub A for asymptote, is going to be 2L plus 1 times 180 degrees. It's an odd multiple of 180. And how many of those angles we have obviously depends on our pole zero excess. If we start with little l, the index on those angles being 0, then we're going up to p sub z minus 1 of those L indices. If we had a pole zero excess of 3, then L would be from 0 to 1 to 2, which is 3 minus 1. We would have 3 asymptotes. And those asymptotes would be then 180 divided by the 3, or 60, and then we would have 60, then we would have 3 times 60, or 180, and then we would have 5 times 360. That's what the 2L plus 1 is sequencing through. If we have 3 asymptotes for those branches, then they have to be at an angle of 60, 180, and 300. They're going to divide our z-plane into equal parts, 3 equal parts. The asymptotes will be 120 degrees apart from each other. Where we will locate those asymptotes, so this is like pin the tail on the donkey, if you've played those games when maybe this weekend. But now we might have that tail. We want to know where do we pin it on the real line so that we know where to draw those asymptotes. That's determined by the centroid, which we are calling sigma sub A. And sigma sub A is determined by simply summing up all of the poles values minus the sum of all of the zeros angles. I'm sorry, zeros locations. Did I say angles? Poles value, not angles. The sum of all of the poles values minus the zeros angles. Zeros value, stuck on angles, shouldn't be because I was talking about asymptote angles, but these are just the pole locations. And do you see that if you had complex conjugate poles, the imaginary or the complex part would cancel? So really you just have to worry about the real parts of those poles or real parts of those zeros. You're summing the pole locations minus the sum of the zero locations, all divided by the pole zero excess. That's rule number 4, and it's just putting on this z-plane guidelines to tell you where those branches are moving or going off to as we crank up the gain k. As we crank up the gain k, our branches of the root locus go off to our zeros. Some of those zeros are finite and some are infinite. Here's an example. Those two poles at the origin are on top of each other. They're at the origin, but I'm showing them separated so that you can see that there's two. And we have a third pole in the right half of the complex z-plane. What's the root locus of this? Or, first off, what's rule number 2 tell us? Do we remember rule 2, or did you forget it after the third exam? You'll have to know it for the final. So now, what's rule number 2 tell us? What's rule 1 tell us? Rule number 1 just says we start on the poles and we end on the zeros, doesn't it? We just put down the X's and the O's. We've already done that in this example. Rule 2 tells us which segments of the real line belong to the root locus. That was rule 2. So now we've cut our bread, and we have certain sections of that bread, and we want to know which of those sections belong to the root locus. Is the section from the rightmost pole to positive infinity, does it belong to the root locus? No, because there's not an odd number of poles and zeros to the right. What about between those poles? So we have a section here, or some of the root locus is there. How many branches of the root locus are there? On that one segment, how many branches of the root locus are on that segment? So we have 3 poles. Well, maybe that we don't want to answer that question until we figured out, is the leftmost piece of our real line belonging to the root locus? It has an odd number to its right, so we do have this going for us. Those 2 real line segments belong to the root locus. How many branches of the root locus do we have total? We have 3 because we have 3 poles. So we have to have 3 branches here at all times. The one on the far right is moving left as we increase k. One of those 2 on the origin is moving to the right. The other one is moving to the left. And what I've indicated in green dashed and with that dot are the rule number 4 pieces. If you now wanted to find the centroid would be, what's the pole 0 excess in this example? 3 minus nothing. So the pole 0 excess is 3. We would sum up all of those poles. Let's say that pole on the right was at 2. So we would now have 2 plus 0 divided by 3. So it would be at 2/3 that this centroid, that's the dot, would be located. And our angles, since we have a pole 0 excess of 3, the fundamental angle, which is this from the positive real axis up to the first asymptote, that's what I'm calling the fundamental angle, will be 180 divided by that pole 0 excess of 3, or 60 degrees. So hopefully you haven't thrown out your protractor after exam number 3. Or you can find another one. So one of our asymptotes is at 60. The other one actually is going off to minus infinity. You can't see that dashed line, but it's going off to at 180. And the other one is 300 degrees from the positive real axis. Question? So our breakaway points and re-entry points, that's rule number 3, apply to poles and zeros. Now, what's going to happen between those 2 poles at the origin and the pole to the right? We have 2 branches coming together. they can't stay stuck at one location, can they? So we have to have a breakaway point between those two values, and the breakaway is not necessarily at the centroid. But we could calculate the breakaway point based on the maximum value of k between the origin and that rightmost pole. And in this case, that breakaway point is probably going to be here somewhere, and this is going to go up and approach the asymptote. This branch is going to go down. It's going to be symmetric. If we put a mirror on that real line, it would see the same thing above and below. And there are 3 branches of that root locus, and that's rule number 4. You wouldn't even have to compute the breakaway point. You could just eyeball it and say, I know the breakaway point has to be, unless I explicitly ask for it on the exam. But if I didn't and I said, give me the rough sketch of the root locus, you could pretty quickly find the centroid and those asymptote angles, sketch those, and now that gives you guidelines with which to sketch the 2 branches that you know are departing or breaking away from the real line between the origin and that rightmost pole. Question? So now the question, I'm trying to get a question out of that comment. So we calculated 3 angles, didn't we? So here is one angle. A second angle is this angle. There's an asymptote. And the third angle, I'm just wanting to play, is there. Those angles are then 60 degrees, 180 degrees, and 300 degrees, where 300 is minus 60. They're equivalent, but this way we can sort of count up to 360 by indexing 2L plus 1 times that fundamental angle. Typically, I'll just say, what's the fundamental angle? And that's the 180 divided by the pole zero excess. And that gives us now this first phi sub A, and once we have that, now we know all the others equally cut up the z-plane.
Why do we allow ourselves to reach the 180 asymptote? The definition of asymptote is something we approach, but
so now the question was, I'm confused by your definition of asymptote, because asymptote usually we think of, we never reach. Just glance over that never reach. In some cases, we are exactly on the asymptote. Okay, we're just calling that because it's a general descriptor. But in this case, one of our asymptotes we're always living on. When we have, well, I shouldn't say that, but if we had 2 poles and only 2 poles, what do you already know happens? When we have 2 poles, they go up and down, don't they? Plus and minus 90. They are living on the asymptote, always. But if we had 4 poles and 2 zeros, we might have 2 asymptotes, but we wouldn't necessarily always be living on those. We might break away and then approach those asymptotes. This, pardon? What is L? L is just an index. L is just, where do you want me to define L? If we define L, or if we're talking about L in the definition for our asymptote angle, L is just an index. And it goes from 0 to 1 to 2 up to the pole zero excess minus 1. And that defines or tells us how many asymptote angles we have. In this second formula for the centroid, I'm just using it as my index on the poles. And now you have to know by the context that that index on the summation of the zeros is not the square root of minus 1. It's just j. I can draw a j better than I can draw a k. I apologize. If you're better with k's, please use a k. But I started to use a k and I go, oh, that's ugly. So I just said a j, and they'll understand by the context that that's not the square root of 1, it's an index. Hopefully that's not confusing. Does that clear up what L is? That was rule number 4, guidelines on how to sketch these branches of our root locus that go off to the zeros at infinity. The next rule, this is the fun rule. Well, they're all fun, so I won't qualify any of them as being fun. They're all fun. Rule number 5, this tells us the direction or the angle with which we approach complex zeros or we depart complex poles. I probably just said it wrong in the reverse order, but here's the root locus direction near complex poles and complex zeros. We want to know, how do those branches leave or depart from the poles, because we know our branches leave the poles immediately as we crank up the gain k. So those are our departure angles. Now you can just think you're at the airport and now we're departing from those poles. And then we have arrival angles to the zeros. And these are complex zeros. And the angle with which we arrive and depart is defined relative to this positive real line going to the right from all of these complex poles or zeros. That's how we will measure these angles. And the way that we determine these alpha sub d's, the departure angles, and the alpha sub a, the arrival angles, is using our good friend, the phase angle condition. And we'll show that with some examples in a minute. But here are some pictures, maybe. Two different cases. Can you sketch quickly, without actually calculating the departure angle and the arrival angle, what these root loci might look like from these pole zero patterns? Let's look at the one on the left. What's rule number 2 tell us? How many real line segments are there in this leftmost picture? We have 2 real line segments, one in the positive and one in the negative. Do they both belong to the root locus? Which one belongs to the root locus, the right or the left? It has one pole and 0 to its right, doesn't it? So now we know that we have that part of our z-plane belongs to the root locus. How many branches, root locus branches, do we have in this particular system? So I've heard 3, I've heard 2. Do I have a 0? Do I have a 1? Do I have a 5? I feel like I'm an auctioneer now, but I'm not going to go there. How many branches do we have? What determines the number of branches? Number of poles. We have 2 poles, so we have 2 branches. Wait a minute, we only have 1 segment. So what does that tell us? What's our pole 0 excess? Let's think about that now. 1. So how many asymptotes do we have? How many asymptotes do we, how many zeros at infinity do we have? 1. So we should have 1 asymptote or 1 angle. And if we have 1, it doesn't really matter what the centroid is. There's no point in calculating it. You know that one's going off at minus 180 if you have 1 asymptote. That branch, or that line segment to the left of the origin, possesses 2 branches. We're going to have a re-entry into that line segment. One branch will head towards the origin from the left, and the other one will zip off to minus infinity. What the rule 5 tells us is the angle with which we depart those poles. And the departure angle is measured with respect to this real line segment going off to the positive direction from that pole. And that would be our alpha sub d. So if that was in fact the departure angle, then we would be doing this. As we cranked up the gain k, we would leave that pole at that angle, alpha sub d. So in fact, alpha sub d might actually be more than 90 degrees. It might be 130, 135. It might be zipping more to the left than kind of curling. But let's just, is it clear what I'm meaning by alpha sub d? Alpha sub d is what in this example that I've sketched. It may not be accurate, but what is alpha sub d approximately? The angle in degrees. Probably a little bit bigger than 60, isn't it? 70, 75. So if alpha sub d is 75, that means as I quickly move off of that pole, as I crank up the gain k, I'm leaving that pole at an angle of 75 degrees. But eventually, I'm going to have to bend around because this branch has to come down and re-enter onto that left part of the real line, or the negative part of the real line. So this is going to go here, and one's going to go here, and one's going to go there. And what do we know about the root locus? Once you've sketched the upper half, the bottom half is symmetric. So bear with me. This has to be looking the same, and it would do that. And the way that we depart that complex pole, we're going to calculate as alpha sub d, and that will inform our picture. It will make our picture a little bit more consistent with the real root locus. That's why we calculate that alpha sub d. Did I calculate the alpha sub d? No, I just sketched it. But we will learn how to calculate that, and we'll have to know these actual numerical values for the locations of our poles and zeros to do that. But the way that we will calculate alpha sub d is, now everybody likes epsilon, right? What do you usually use epsilon for? Pardon? Errors? I was thinking of something really small. Ooh, I won't do that again. But if you get really small, that's epsilon, right? Epsilon is typically, sometimes you think of epsilon, oh, epsilon is going to what? 0? We look at an epsilon distance away from the pole that we're wanting to calculate that alpha sub d. Meaning, why are we talking about an epsilon? We want to make the calculation fairly clean or simpler. So now if this, I'm exaggerating, let's say this is now an epsilon away from that pole. If we assume that we're an epsilon away from that pole, what's the angle from this lower pole up to that point, that green point? Well, if I'm epsilon away, I'm essentially at that point in the first quadrant, am I not? What's the angle from here? So I would call this, let's say, theta p sub 1. What's theta sub p sub 1 in my phase angle calculation? If I need to know what's the angle from that pole up to that epsilon point, where epsilon is just an epsilon distance away from that upper pole. What's theta sub p sub 1? It's a very difficult computation. Pardon? Isn't it a right angle? Isn't it 90 degrees? Theta sub p sub 1 is right below, because epsilon is tiny. If we're still an epsilon distance away from that pole, we can immediately calculate the angle from that 0 to that epsilon location. It's basically from the 0 up to that pole. In this case, maybe it's 45 degrees. That's theta sub c, theta sub z. Now we could use the phase angle condition and do what? Now we would say, from the phase angle condition, we would say, oh, theta sub z, how would we continue? We have the sum of our zeros minus the sum of our poles, angles, and now we have to say, oh, the reason I'm going an epsilon distance away is now I can measure the angle contributed by that pole in the first quadrant. I'm assuming I'm on the root locus, which is an epsilon distance away, and so that angle will be alpha sub d. plus theta sub p sub 1 is equal to minus 180 degrees. So if this was drawn to scale, I would say theta sub z is 45 minus alpha sub d minus 90 degrees equals minus 180. I've now calculated my departure angle. Do you follow how I did that? This is just the algebraic sum of the angles of G equaling minus 180. We know that has to be true for those points to be on the root locus, and that epsilon belongs on the root locus. So you can do the math for me, but this is 45 degrees. This was 90 degrees. And alpha sub d, if I push it on the right-hand side, I have 180 plus 45 minus 90. I have 180 minus 45. So alpha sub d is 135. So in fact, I should be going off at that angle from that pole, based on if this diagram is sketched accurately. That alpha sub d needs to go all the way through an angle of 135 degrees, which is 45 degrees shy of 180. 180 would be I'm zipping straight off to the left. 270 would mean I'm going straight down. 90, I'm going straight up. 45, I'm going off closer to what I drew initially. Is that clear, the departure angle? If not, talk to your buddies tonight, because I know you're not going to sleep until you figure this out. Okay, so we want this under our pillow tonight, thinking about poles and zeros, departure angles and arrival angles. How do we arrive at those zeros on this rightmost picture? First, let's figure out which segments of the real line belong on the root locus. Between the right two poles, I'm giving you the answer for one. I'm just assuming that we're not on the far right of the real axis. We have a segment there. We have a segment here. How many branches of the root locus do we have? 3. I see 2 segments. Huh? Where do I have 2 branches? This guy is going to the right, this guy is going to the left. They are breaking away, and you could calculate the breakaway between those poles by calculating the relative max of k between those numbers, between those values of z. Then what happens? Well, then they leave and arrive at those zeros. 2 branches have to terminate on the finite zeros. And where's my other 0? It's off at infinity. What's my pole 0 excess? 1. What's my fundamental angle of my asymptotes or tote? 180 divided by that 1. It's 180. So I know I have one asymptote, and it's at 180 degrees. The angle of arrival, the way I've sketched it, is right there. I would draw the line tangent to that red branch and measure that angle between this positive real segment and that angle. Alpha sub d, the way I've sketched it, is about 45 degrees. Whether that's right or wrong, I could calculate. Because I can numerically, if I've given all of these values, I can measure or analytically compute this angle from that pole. I can calculate the angle from that pole. I can calculate the angle from this pole, and I can calculate the angle from that 0. And I'm calling alpha sub A my unknown. I don't know what that angle is, but all the others I can compute if I know those locations for all the other poles and zeros. That's rule number 5 in a nutshell. But you can now go home and play with your protractor or your calculator to do the trigonometry. I was talking to some high school students this weekend, and they said, how can we prepare for engineering? I said, learn your trigonometry. And I got the weirdest stare or glare. But it's important, isn't it, for complex numbers to be able to use your trigonometry. Little did you know when you were doing sines and cosines in trigonometry that it would become so second nature as an electrical and computer engineer. Oh, what happened to our example? Let's cook up an example. So now let's find or try to get some insight into where rule number 4 is coming from. What's rule number 4? What is it concerned with? The asymptotes and their angles and where they're located. Suppose that I give you the following pole 0 diagram. Let's say that's the pole 0 diagram, and what I'm really wanting to do or learn from rule number 4 is if I went away from this 30,000 feet, what's the 30,000 foot view of this pole 0 pattern? What does it really, how can I approximate the behavior of these 3 poles and 1 0? What do they really look like if I'm really far away? That's what the asymptotes are going to produce or provide me with, is that information. Here's the question. Far away in a z-plane, far, far away. I feel like I'm reading a bedtime story. We were already talking about sleeping, right? So, ooh, don't fall asleep. But far, far away on the z-plane, we're trying to figure out the behavior. Far away, what does the pole 0 pattern that I've just sketched what does it look like? Maybe you can't see my notation, but I put some eyes on that look. Oh, you were falling asleep, so I had to wake you up. Huh. Now, from a faraway distance, here is what I'm suggesting is the approximate behavior. If you now were way far away from that pattern, sort of what would the average behavior look like? If you had to now approximate that, you were standing a long way away in the z-plane, how would you approximate that pole 0 constellation? How would you simplify it here in this z-plane? How many poles do you have? How many poles do you have? It can't be that hard, is it? Unless you're just waking up. How many X's do I have on that diagram? 3. How many zeros? 1. So the net number of poles, net, not that net, but the difference between poles and zeros. We've passed beyond the basketball season, haven't we? For college. So we now have 2 effective poles. Yes? And if we're way, way far away, maybe we just put those poles somewhere, like at a centroid location, and say, oh, this is what they would look like. This pattern. From a far distance, it would look like two poles at some location in the complex z-plane. We're just averaging, essentially, or trying to get a rough feel for what's happening. So now, is it okay that I would locate those, and they would now be located at sigma sub A? And what do I know the behavior of this would be? Well, now if I just have two poles on top of each other, I know that they're just going to go zipping apart as I get K bigger and bigger. And these dashed lines would then be my asymptotes for the approximate behavior of that three-pole 1-0 pattern far, far away. Now, how do I know that that's true? If I put a point there, what do I know? If that belongs to the root locus, what do I know has to be true about the point, that red dot? Or, let me step back and I say, I want to know, based on that red dot, what's the angle from the topmost pole, and those poles are on top of each other, but I've now shifted them, offset them. From the top pole to that red dot, what's its angle? Can I just label it? Couldn't you just say that this is that angle? What's the angle of the bottom pole to that dot? Isn't it the same? If I had to turn from the positive real line and point at that red dot, wouldn't it be that angle, theta p sub 2? Now, what do I know about those angles? And in fact, I now could think of this as an approximation. I have z minus sigma sub a squared. That's what the approximate transfer function would look like. Two poles located at a real value of sigma sub a. And what do I know about those angles, theta sub p1 and theta sub p2? They have to satisfy the phase angle condition if they belong to the root locus. I have no zeros, so I have nothing minus theta p1 plus theta p sub 2 equaling minus 180. And theta p1 is exactly the same as theta p2. So I really have minus 2 theta p1 is equal to minus 180 degrees. Or I can divide both sides by 2, just doing some algebra. I now know that theta sub p1, which in fact is the fundamental angle of that asymptote, phi sub a, is equal to, I lied, I'm dividing by minus 2 on both sides. I now have 180 divided by 2, or minus 180 divided by minus 2, or my asymptote angle is 90 degrees. So far, far away, that three-pole 1-0 looks like a two-pole system with the asymptotic behavior determined by the centroid of those two approximate poles and their asymptotes, which are at plus and minus 90 degrees, or 90 and 270. General formula. The centroid, sigma sub a, that's what we're calling it, the centroid of the root locus asymptotes, that's in fact the real line or real axis point where these asymptote angles are centered. And we compute that formula-wise is going to be the sum of the poles minus the sum of the zeros, all divided by the pole zero excess. That's the centroid. That's where we pin the center of those asymptotes. Like pin the tail on the donkey, we're pinning these angles, their center, at a particular point on the real line. And we can compute that by just adding up all the poles, subtracting all of the zeros, and dividing by the pole zero excess. And these angles of the asymptotes are given by an odd multiple of 180 degrees divided by the pole zero excess, where L assumes values up from 0 up to the pole zero excess minus 1. Let's look at a particular example. I've been talking in very general terms. Let's look at a more specific example as it applies, or as we apply rule number 4. Suppose that g of z is now 2 over z plus 1/2 z minus 3/4 and z minus 1. Hopefully you're already seeing the pole zero pattern in the z-plane. But if you're looking for extra credit on the final, what do? You immediately start saying, what's my pole zero excess? That tells you something useful about sketching this root locus. Pardon? You're wanting partial credit? So now we have what? The pole zero excess is 3 minus, we don't have any zeros, so it's going to be 3. Now we can talk about our asymptotes and we can calculate the centroid. But the asymptote angles what's the formula? That's now 2L plus 1 times 180 degrees all over PZ sub E for L equals 0, 1, up to 2. Where that 2 is our final L, which is PZ sub E minus 1. 3 minus 1, 2. This math is over the top in terms of complex, isn't it? 3 minus 1. Not much of a joke, was it? So, what's the fundamental angle? L equal to 0. 60 degrees, that's when L was equal to 0. And if we wanted to, we could compute the others. We have 2 times 1 plus 1, that's 3 times 180, divided by 3. So this is just 180 degrees, and that was when L is equal to 1. And finally, we have 5 times 180 degrees divided by 3. And now you might just say, oh, that's 60 degrees times 5, or that's now the 300 degrees, and that's L equal to 2. Those are our asymptote angles. And what's the centroid? We now have this pattern of asymptotes, one at 60, one at 180, and one at 300. We want to know, where do we pin that on the real line? And that's determined by the centroid. And the centroid, I just sum up all of my pole locations. Where were my poles located? Now you just have to pay attention to the sign, S-I-G-N, of those values. You have 3 poles, no finite zeros. So the contribution due to the zeros is not going to be any. But we have a pole at, working from negative infinity to the positive. Where's our first pole? Minus 1/2, then 3/4, and 1. Or now we can say that we have minus 1/2 plus 3/4 plus 1 minus, I'm going to say nothing, divided by the pole 0 excess, which is 3. Or I now have effectively 1/4 plus 1, or 5/4, divided by 3, or 5/12, so something a little bit less than 1/2. A little bit less than 6/12. And if we compute that, sigma sub A would actually be 0.4167. And now we can actually sketch without too much effort a reasonable picture of this root locus. I had a pole at minus 1/2. I had another pole at 3/4 and another pole at 1. Where's my centroid? So it's 80% of the distance to 1/2, isn't it? 82%. But we're now going to say it's right there, and I need to go at 60 degrees and 300, or minus 60 degrees, which that's probably not quite 60 degrees. But do you see that this segment belongs to the root locus, as does that one? This one's going off to 180. These two will break away. One will approach that asymptote. The other one will approach that asymptote. And that's a quick sketch of that root locus. And if we wanted to fine-tune that, what would we be interested in? Based on this root locus, maybe somebody wants to know something about stability. Based on this quick sketch, can you identify stability boundary points, or points on the root locus that would indicate where we cross from being stable to being unstable? Based on this sketch, what do we need to focus on? We need to worry about the unit circle, which is right there. There's our unit circle. And now if we've sort of sketched this somewhat effectively, we know that we have one point there when we exit the unit circle at -1, and another point right there. And if I've sketched that somewhat accurately, which I probably haven't here, you might be able to sort of eyeball this and say, oh, z delta is approximately 0.9. It's maybe a little to the right of halfway between 0.75 and 1. So let me say it has a real part of 0.9, and maybe, wow, I'm getting really accurate, 0.43 for J. But how would I find where that actually breaks away between 0.75 and 1? How do I find that breakaway point? Now I'm looking for more details. What do we use to determine the breakaway point? Pardon? The geometric mean. We use the geometric mean to determine a breakaway point when we had what pattern of poles and zeros? When was that in play? When did we worry or use that? And that was actually a special case when we could use the geometric mean, wasn't it? That when we had 2 poles and a 0, where the 2 poles were to the right of that 0. Now what we're looking for is the relative maximum of our gain k between 0.75 and 1. Right? We're hanging posters again. It's Monday about 6:30 local time. I'm guessing you can't pick that up on the microphone, but I can actually hear that, which must mean it's pretty loud. How do we calculate the breakaway point? We want to know what's the k between 0.75 and 1, and we're looking to find the maximum of that k value. Yes, so now the answer to that question was, can we use the magnitude condition? Can we set the magnitude of kg equal to 1? And in fact, that's what we would do. We now say k, and g was 2 over z plus 1/2, z minus 3/4, z minus 1. That magnitude needs to equal 1. And now what do we do? Well, first I would solve it for k. K I'm assuming is positive, so it pulls out of the absolute value symbols or operators, and we can put all of that other stuff on to the right-hand side of that equality sign, and we have the magnitude of z plus 1/2, z minus 3/4, z minus 1, all divided by 2. And now you could number crunch. You could plug in particular values of z and look at how k varies. And you're only looking at a short region in the z-plane between 0.75 and 1. You know somewhere between that you're going to have k hitting a relative maximum. And what happens at the relative maximum value of k? That's the breakaway point. And you would say, oh, for that z, that's where I break away from the real line. That's the biggest k that I can get to before I start leaving the real line. That's my breakaway point. In this case, let's say that we've already done that, and we see that we have a relative max of k at z equal to 0.881. So we're breaking away very close to 0.9. And we could now plug in that k value to that formula. We've already done it probably if that's the place where we hit the maximum, but we now evaluate that for k equal to I'm sorry, for Z equal to 0.881, and we get K equal to 0.011 at the breakaway point. So we don't have to crank up K very much before we break away from the real axis with those two poles at 0.75 and 1. What should we do next? Well, it might be nice to know we know that the K value to get to the triangles is where? How big is K to get to the triangles? We know it's bigger than 0.011, right? Because now 0.011 gets us to the breakaway. We have to crank it up more to get to those triangles. What we would like to know maybe is, have we already snuck out the unit circle at -1? It's not too hard to calculate the gain K at -1 because we already have the formula for K. So let's compare what gain does it take before we escape out of the unit circle at -1? Because we know that we need to figure out where those branches are relative to the unit circle and what magnitude of gain K gets us to those points. So now let's look at K when Z is equal to -1. This is now going to be -1 plus 1/2, -1 minus 3/4, and -1 minus 1, all divided by 2. Or 1/2, 7/4, and 2, all divided by 2. Upstairs, I have a 1/2 times 2. That goes away. And I now have a 7/4 divided by 2, or I now know that the gain to get me to the unit circle at Z equal to -1 is going to be 7/8. That's quite a bit bigger than the gain to get me to the breakaway point, isn't it? So I'm going to crank up that gain quite a bit before I escape out of the root locus at Z equal to -1. But can I go as high as 0.875 and still be stable? I've learned that K here do I need to find another K value to determine stability or to verify stability? I'm trying to find the range of K to keep my closed loop system stable. I know that I can be between 0 and 0.011, obviously. What I'm asking now is, can I crank it all the way up to 0.875? And how will I check that? I now need to check what's the gain to get me to that triangle. Either triangle, up or down, and I'm just going to do the one up. So now I want to know what's the gain K at the triangle. So now it's Z -1, Z minus 3/4, and Z plus 1/2, all divided by 2. And now I just eyeballed that, but that might be good enough to give me a good ballpark number on the gain. And I said that was 0.9 plus J 0.43. I'm going to just tell you what that ends up being, 0.1472. So what's my range for stability? It would be from 0 all the way up through 0.011 up to, well, this maybe is not quite right because I just eyeballed that, didn't I? Let's look at the closed loop poles maybe for that value of gain and see where I live relative to the unit circle. If I now examine stability for that gain value, let's do that by looking at the closed loop poles. What's that formula look like? What's the expression for my closed loop poles? That's my denominator. I'm trying to find the values of z that cause that to vanish. For my system, it's 1 plus 2k over z plus 1/2, z minus 3/4, z minus 1 equaling 0. Or, if I look at the numerator of that expression, that will be my characteristic equation. Which says that I'm now looking at z minus 1, z minus 3/4, z plus 1/2 plus 2k is equal to 0. And I want to now evaluate that at k equal to 0.1472. That was my eyeballed estimate and calculation of the gain k. If I find the values of z that cause that to vanish, I end up at 0.94 plus and minus j 0.42, so I really wasn't too far off with my estimate, and minus 0.631. So I haven't yet gotten beyond minus 1, which I knew because it takes me a k value of 0.875 to get that far. And I didn't move very far from minus 1/2. I only moved to minus 0.63, cranking up the gain to a value of 0.15. But I can now more easily compute the magnitude of this. Pardon? What is the minus 0.631? Can you help us? What is minus 0.631? Is it clear that for a gain value of 0.147, that's now found locations on the root locus? As I crank up the gain k, I move on these red branches. And if I crank up the gain k to 0.1472, I move to where? I actually am moving a little bit beyond that triangle. I'm moving out here and here. And how many closed loop poles do I have? 3. And so I'm actually moving another one right there. And this is at minus 0.631. These clouds are the 0.94 plus j 0.42. So that's the gain k, and that's getting me a little bit beyond the unit circle because I calculated the magnitude of those clouds, and they ended up being a magnitude of 1.03. So that's a little bit beyond my stability. Suppose I pick a gain of 0.011. Well, what would you pick for a stable upper bound? Now that you're getting close to being full-fledged engineers, you have your cap on, you're now an engineer, almost graduated. What would you pick for a gain of K for stability based on the analysis that we've just completed? What would you feel comfortable walking into your boss and laying on her desk and saying, okay, here's the K values for stability? You would say, I don't know, I had THARP for 442, give me a break. Right? No, don't say that. You could, I guess. Oh. But what would the gain be? Would it be 0.14, 0.15? Would you tell that was a stable value for K? Not after checking. You know this characteristic equation is valid if indeed it's modeling your system. And for K equal to 0.1472, boom, now you know exactly where the poles are. Forget this eyeball stuff. This is now where they're at. And we can calculate the magnitude of those and determine, are they all with a magnitude less than 1? And in fact, 1 is not. 2 are not, aren't they? They're complex conjugate poles. What have we learned? We can't go that high with K, that knob K, and remain stable. What might be an acceptable upper bound? We don't know it exactly, do we? So you might actually go back to your desk if you felt a little bit uncomfortable and do a few more calculations. You should what? Roll back on that gain value K. Roll back. Maybe K equal to 0.1. I don't know. Pick a number, right? But you know it can't be 0.15. It can't be probably 0.14. So let's just make the following decision and say that. You could check to see, how would you check if that's a okay upper limit for stability on K? Let's say that this is now the stable upper bound on K. Must check or must verify. How would you verify that that's okay for K? Okay for K. Now you've got the formula right there. It's probably still in your calculator. Just scroll up, repeat it, and put K equal to 0.11 and see if you get some complex roots. Take the absolute value of those complex roots, and what are you looking for? You hope that computation yields a magnitude less than 1. All right, now let's say that somebody wants to know how long is it going to take for this system to stabilize, or I'm sorry, to reach its steady state. How long of a transient am I going to have for this system? Well, somebody's going to have to give you a K value, aren't they? So now let's suppose that somebody says, oh, let's use K equal to 0.011. I like zeros and ones, apparently. I must be doing some computer engineering stuff. Zeros, but this is a decimal, isn't it? It's not binary. But it's 0.011. Do you remember where that came from? That was the breakaway. So what are my poles now? Why would I maybe choose K equal 0.011 if I was interested in settling time? Those two are real, aren't they? What's the third one? It's real all the time, isn't it? So I have 3 real poles if I pick a K of 0.011. And if I have real poles, how do I decide on settling time? Suppose K is equal to 0.00011. This you just told me is the gain at the breakaway point. And that value of gain K will produce 3 real poles. Where's my dominant pole? Pardon? My dominant pole is at 0.881. Why do I know that? Because I know at a gain of, where was I? 0.14, my pole was at minus 0.63. That's inside 0.881, and I haven't even gotten to that large of a gain to get me to the cloud point, have I? So I know that my dominant pole are the two that are real at 0.881. And do you know how to calculate settling time given a dominant pole? Exam number 3. So that if you solve for n sub s, what's your settling time? $37. You go running into your boss, and you go, I have a settling time of 37 sample periods. And your boss goes, that's too slow. And then what do you do? You turn in your letter of resignation? No, you don't do that. You pull out your letters, don't you? PID. Maybe you do a PID controller. So we'll pick up there maybe next time. I still wanted to do the rule number 5, but we've already covered that a little bit in the overview. So we'll figure out where we want to go from here, but that's where we're at.